In this work, we introduced a novel method for an overtaking algorithm in autonomous racing, where we use F1TENTH as the racing car by using recurrent neural networks in a machine learning model. Here, you can see a red car driven by a fully autonomous agent that's making use of our overtaking algorithm, and a blue car which is manually being driven by a human. The red car will try to overtake the blue car without any collision. F1TENTH is a small-scale Formula 1 model with LiDAR and camera as perceptors and an embedded computation unit. In this work, we will only use LiDAR as the main sensor. Due to time constraints, we haven't fully tested our overtaking algorithm in the real world. So most of testing is done in a two-agency simulator which developed by us as shown in the previous video. Before we could train a model, we needed a two-agency simulator that can simulate two F1TENTH model cars at the same time. We used a single-agent simulator as the base and extended it to a two-agency simulator. To do this, first we add a box collider, which allowed for collisions to be replicated within the simulator, indicating that the algorithm was unsuccessful. If a collision takes place, the cars stop, giving us information on the simulation in the terminal. In the real-world computation, the LiDAR is able to detect a second car in front of via an appended box, as you can see in this picture. To replicate this in the simulation, we've ensured that the LiDAR can only pick up the rear and the sides nearby, as would be the case in the real world. A lot of work has been in the tire model, ensuring that the effect seen on the left, where friction doesn't reduce speed at a turn, does not take place in the simulation. We implemented the model predictive control algorithm as a line follower for letting one car driving autonomously. For the yellow dot line, we used a package called Global Race Trajectory Optimization, which can produce a minimum time trajectory for a given racetrack. The purple dot, one of the points in the minimum time trajectory, represents the goal of MPC algorithm. The reason we used the MPC algorithm to control one car is because the imitation learning approach is used. We want one car driving autonomously and the other car driving manually while collecting data from the manually driving car, so that a machine learning model can copy behavior from the dataset. Here we can see a table of generated data, which highlights that we trained the model on 4 different real-world F1 Grand Prix racetracks, replicated in the simulation, with following columns depicting training instance for each racetrack and other related attributes of the data. Each row's number of file number is 3 times the instance value, as each instance is comprised of 3 files that hold the related data. To generate the learned behavior from the user-generated overtaking behavior, we consider 2 sources of inputs. Here, these are seen as input A and B. A is the larger input, as it takes into consideration LiDAR data from different timestamps from the manually controlled car, resulting in 1081 columns, this being each LiDAR steps, and rows representing a given time point with respect to each of those LiDAR steps. Input B, on the other hand, is a record of the car's real physical attributes, those being speed and steering angle. Since input A is large, we employ an embedding layer, which reduces the dimensions of data worked on. This simply allows for increased levels of overtaking performance. This idea is taken from natural language processing, where sequence-to-sequence problems are similarly solved as in our project. The RN layer is used because it's a method for working with high quantities of timestamp data, again as with natural language processing problems. It has the added benefit of remembering information gathered after each timestamp calculation. After working on input A, both inputs are then concatenated into one single input, where this is in turn worked on via multiple dense layers. The output is two columns, speed and steering angle, with the same shape in terms of rows as the input data. Here we can see the actual code used through the Keras in TensorFlow package. Both simple RNN and LSTM neural networks can be used for creating a successful overtaking algorithm. However, we prefer the use of the former due to higher overall success rates in experiments performed with the simulation. This can be seen in this example video, where the car does not overtake as efficiently and swing more radically when trying to overtake, whereas the simple RNN steers more cleanly. Here in the video, we can see that the autonomous car employs the overtaking algorithm when in the second place. And when it achieves first place, it sticks to the optimal path for the best time by using the MPC algorithm. When compared to entrance to the IROS 2020 F1TENTH computation, our results were comparable to those in second place. Thanks for watching.